Hello, and thank you for watching. This video was made with the design demonstration and verification submission for ECE 5000. The project chosen was the Treadmill Tracker, which is a self-contained speedometer and odometer for a treadmill that allows the user to read workout data on an attached LCD screen, an Android app via Bluetooth, and on a computer through a text file stored on an SD card. This video will cover a detailed explanation of the communications block diagram, the electrical and mechanical specifications of the project, a walkthrough of the tracker's code, a step-by-step explanation of the design process taken, a demonstration of all the included features, and finally, a conclusion and recommendations. Here we can see the communications block diagram for the treadmill tracker. Here in the middle, we have the central casing, which houses an Arduino Uno, the power supply, and all the main circuitry of the product. The power supply is a 5-volt rechargeable power bank, which has an average life of 10 hours and can be charged in 3. Shown on the right, the product has a Hall effect sensor that can read changes in magnetic fields. Pairing this with a magnet attached to the treadmill belt, it can read the number of passes and speed between passes. The Arduino then uses this information to calculate the distance and speed. On the central casing, there is an LCD screen that displays the total distance, current speed, and messages depicting the status of the workout. The Arduino stores all workout data on an SD card, which can be plugged into a computer and saved there for further use. There are 2 input buttons, one which allows the user to pause/resume workouts, and the other ends the workout and preps the SD card for ejection. There are also 2 outputs in the form of LEDs that warn the user of a missing SD card and displays the current status of the workout. At the top, there is a Bluetooth transmitter that can send and receive data from an Android app on the user's smartphone. The app displays workout data in real time and allows the user to pause, resume, and end the workout remotely. To pair a phone to the product, simply power it on, select HC06 in the phone's Bluetooth menu, and use the password 0000 or 1234 to connect. The following charts show the electrical and the mechanical specifications of the tracker. The Arduino has a minimum working voltage of 6, a maximum of 20, and typically runs between 7 and 12 volts. The system can draw a maximum of 255 milliamps, 200 of which is drawn by the SD card at max draw, which only operates at the end of each workout, meaning that the typical operating current is much less. The power bank has a charging current of 1 amp, a charging voltage of 5 volts, and can be charged using a standard micro USB cable. It has a capacity of 2,600 milliamp hours and takes 3 hours to charge to full. Using the max current draw and battery capacity, we can estimate the minimum lifetime to be around 10 hours per charge. This can be increased by turning off the power bank between workouts by holding the button on its side. The product is 195 millimeters long, 135 millimeters wide, and 70 millimeters tall. It weighs 435 grams, and to mount the product, a non-slip material was added to the bottom to keep it from sliding off of the plastic treadmill casing. The Hall effect sensor and the magnets are fixed to the treadmill using tape. All coding for the tracker was done on the Arduino IDE. For organizational reasons, the code is broken up into multiple functions that tend to pertain to different sections and features of the product. The code starts with all the necessary variables defined and grouped based on its uses and the components/features they apply to. The setup function initializes the overall timer, the serial port, the output-input status of all ports used, and the LCD screen. The speed function, shown here, is called once per loop. It reads the current state of the Hall sensor and compares it to its previous state. If it is now low and was high, it takes the time of the current and previous readings and uses them with the length of the belt to calculate the current speed and average speed of the entire workout. The Bluetooth function is called once every 10 loops. It formats the data to be sent to the app. It is not called every loop, as the speed at which data can be received on the app is much less than what can be sent from the Arduino. The data log function is called at the end of each workout. It formats the data into a workout summary and prints it to a text file on the SD card. The remaining loop function contains the majority of the coding and logic for the tracker. This first section reads the start button and determines if a workout is starting or resuming based on if loops have already been counted. Then we enter the workout loop. This block checks if the SD card is missing. If so, an error message is thrown and prevents the workout from starting. If not, it continues. Here, we turn on the green LED to show the user that the workout is active and data is being recorded. This block reads data sent from the app to determine if one of the buttons was pressed. The speed function is then called. Here, the distance is calculated, and the speed and distance are printed on the LCD screen. This calls the Bluetooth function every 10 loops. This block reads the pause variable to determine if the physical or remote button has been pressed. And this final block checks if the user wants to end the workout. It calls the data log function and resets all necessary variables to prep the tracker for the next workout. The app was made using MIT App Creator. This program allows creators to make an Android app using a library of assets that can be dragged, dropped, and customized in the workspace. All features were coded in Scratch on the program. These two blocks code the list picker entity to work with the available Bluetooth devices on the smartphone to be able to connect to the Arduino. This section receives a string from the Arduino, splits it into a list, and prints each item individually in the labels for users to use. And this last section determines when the buttons are pressed and sends a character to the tracker to be interpreted there. The design process started with the basic idea of making a speedometer and odometer for a treadmill. Components such as the SD card reader and Bluetooth transmitter needed to be included as well to add remote interaction and data logging capabilities. From this base idea, extra features were brainstormed to increase the utility and value of the product. One extra feature in particular that made it into the final design were the start/pause and end buttons on the main casing and remotely from the app. There were a handful of features that didn't make it to the final version for multiple reasons. One was a timeout feature that would power down the tracker and end the workout after time has passed without readings from the hall sensor. This was later decided against, as the user could have reason to keep the tracker going without the treadmill. For example, if they wanted to take a short break, but include it in the timer to keep workout data accurate. When implementing each component into the design, each one was coded and tested individually to gain a better understanding of how they worked. Then, one by one, they were added to the tracker, testing after each one to make sure they worked together. The distance and speed capabilities of the hall sensor were first to be added, followed by the buttons, LEDs, the SD card reader, and finally the Bluetooth transmitter. One major design challenge that needed to be overcome was fixing the magnets to the treadmill belt. Multiple magnets were tested to find ones that were strong enough to be picked up by the sensor at high speeds, but light enough to not have inertial effects on the belt. This problem was solved by breaking up a strong neodymium magnet into 6 smaller pieces and taping them to belt in a straight line. The reason 6 were used was because at higher speeds, the hall sensor had trouble reading them. Adding more in the line widened the magnetic field and in turn made the window that the sensor could read larger as well. When wanting to start a workout, The user will have to open the casing and turn the power bank on by holding the button on its side until the screen turns on. Now, the tracker is ready to start. The demonstration will begin with showing off the effectiveness of the SD card warning. When a workout is attempted but the SD card is missing, the screen will flash a warning and the red LED will blink. A similar warning is thrown when the SD card is removed in the middle of a workout. Now, once the card is reinserted, the green LED turns on and it's ready to start taking data. We'll start the treadmill on its lowest speed of 1. Short disclaimer, the treadmill used is quite old, and its odometer no longer works. And although it was researched thoroughly, the units of speed it uses remains unknown. Up until now, miles per hour were assumed, but it has since been decided it would be inaccurate to say that. The built-in speedometer will still be used to compare the trackers. Now, let's increase the speed to 3. Before we go any further, let's show the effectiveness of the pause feature. As you can see, no data was taken while the tracker was paused. So let's continue increasing the speed, this time to 5. And finally to 7. Let's remember the distance of this workout so we can compare it to the SD card to prove its accuracy. Once the workout is ended, we can remove the SD card and insert it into our computer. If we select the data log text file, we can see our most recent workout appears at the bottom. And as you can see, the total distance matches what was said. Now for the Bluetooth functionality and the Android app. Once the HC06 is paired to the phone in the Bluetooth menu using password 0000 or 1234, we can open the Treadmill Tracker app and select it from the drop-down menu. Let's keep the treadmill at a speed of 5. The speed at which the app can receive data is much slower than what the Arduino can send. To stop this from causing errors, the app only updates once every 10 loops of the belt. We can also use the buttons on the app to pause the workout, resume it, and to end the workout. In conclusion, I'm happy with how the tracker has turned out. I'm happy with all the features that made it into the final design. I wish I was able to add more, but in the end it came down to time, but I am proud of what I've made. If I were to have any recommendations for someone who would like to try a similar project, would be to explore different sensor options instead of the Hall effect sensor. My biggest struggle was attaching the magnets to the belt in a way that would work effectively at higher speeds. Look into color sensors or infrared sensors to see if they would work as well or better. Thank you so much for watching.